Hi, my name is Holden Cooper, and during my multidisciplinary capstone this year, I worked with GFR and created the driver interface electronics. The main goal of the project was to make the steering wheel and dashboard electronics for the GFR 25 electric race car. The main design goals were simply make it smaller, make it more reliable, and make it more comfortable to use, more ergonomic for the drivers. Some of our inspirations this year were this F1 steering wheel from McLaren, as well as the Fanatec racing simulator wheels. So for this year's dashboard, we simplified it. The main changes that we made were that we removed the dashboard display and we added additional LEDs and drivers. Now these LEDs and drivers ended up being on the dash breakout, which allowed the dashboard to be extra thin this year. During this process, I did the component selection and schematic design, and then I passed it to Will Dixon, who finished the project doing the PCB design, manufacturing, and testing. And that can be shown on the flowchart. The blue block firmware design went mostly to Pavlo, who is the lead of the firmware design team for the car. For the steering wheel, I was the producer of all of the chunks of the flowchart, starting with component selection, schematic design, but continuing with PCB design, some firmware design, manufacturing, and testing. So the main changes that we made to the wheel this year were we wanted PCB mounted buttons. So we wanted those to be attached without loose wires and less soldered connections in that way. And then we also wanted, the same for rotary switches, anything that the driver interacts with. We wanted an integrated display in the steering wheel, and we wanted to try to improve reliability by potting or encapsulating the steering wheel. For the schematic and component selection for the dashboard, we utilized many previously used system blocks, but new components were used. So the first thing we changed was the power supply, which allowed for a reduction of components. We also added new LEDs, and from last year, we had a comment from a judge that told us that our LEDs on the dashboard were not green enough, and they looked amber, and so we decided to switch out some for more distinctly green. We also added a connector for the racing switch, and we added two new connectors for the steering wheel and the steering wheel and the dash breakout board to be attached to the dashboard. On the right, there's a top level dashboard schematic. So here are the changes we made to the schematic. On the right, so we added a steering wheel connector, which connects vehicle CAN and our two vehicle CAN signals, as well as 3.3 volts in ground. And then for our breakout connector, we did the same thing. And then for the SDC header, which is a large connector on the board, we opted to connect a race switch part. And so in that schematic, there is a pull down resistor that I added this year that should help with the connectivity of that race switch. For the dashboard, we also included the dash breakout subsystem. For this subsystem, we primarily decided to use the same circuitry we had used in previous years, but we multiplied it by 2. We added more LEDs to allow for more status messages to be delivered to the driver. This is the schematic for that, and for the most part, it's not much changed, besides that we have separated it from the other board. We also made changes to the power supply. This power supply is from Worth Electronics. It is very similar to the previous one, but it doesn't have the customizability of voltage output. And because of that, we only need a 3.3 volt output. So it has a 24 volt or plus, I think, 24 volt input, 12 volt input to a 3.3 volt output. So it's just a great simplification to what we had previous years. The rest of the components are reused from GFR 24. We use the same microcontroller, CAN transceiver, oscillator. Everything in this has basically remained the same since last year, because these are the sections that work. For the steering wheel, we yet again used many of the GFR 24 subsystems, but we used a lot of them from the dash, creating a whole new board that fits inside the steering wheel rather than having a very small breakout board that's connected to the dash. So we included new parts, especially for the driver interface sections. We added external pull-down resistors for buttons, and then we also added an analog voltage isolation and the rotary switches for resistor networks. Now we also added the display in, but the display reuses the flat flex cable connector, FFC connector, that the dashboard used, which is why it's not included here. But we do include a display in the steering wheel, which is distinctly different from last year's steering wheel. On the right, you can see the schematic for the top level, and then each of those green blocks connects to a smaller schematic that represents a specific system. So here's one of the systems that I designed. This is the rotary switches system. It uses a resistor network as well as some analog filtering to reduce switching noise when these rotary switches are turned. Both of these resistor networks have been simulated and made sure that they work. The next thing that I just recently talked about is the steering wheel. In the steering wheel subsystem is the analog voltage isolation. So on the bottom left of the schematic, there is some new circuitry that was taken from the PDM instead of the dashboard, and is used to isolate an analog plane from the digital plane. And by doing this, we can reduce the amount of noise that our digital signals are basically small square waves, small pulse waves, have on switching, which can really affect it. So we added this just to be certain that our rotary switches would behave properly, and we made sure to route them in the traces and the PCB accordingly to reduce that sort of switching noise. And then lastly, we added pull-down resistors. For each of the buttons, there are internal pull-down resistors within the microcontroller, but we opted to use these instead because it adds a little bit more robustness, and it reduces the firmware complexity by very slightly increasing hardware complexity, which we felt was worthwhile. The remaining components were all reused from the dash of GFR 24. Originally, we were going to switch the power supply to be using the same power supply as the new dashboard, but we actually had a height constraint to fit within the steering wheel enclosure, and so we opted to use this one instead. Though it adds more components to the board, it does improve that vertical fit challenge that we had earlier. Everything else is the same. We have the same CAN transceiver as well, same microcontroller as the steering wheel from 24. The last part of the selection is the display. So we chose to go with the EVE3X 35A IPS display from Matrix Orbital. Now this display was useful because it has the same display driver as previous displays we've used. It is a very bright display, and it has color, which means that it's easy to use. Our deliberation about this took a while because we were not certain if we wanted to have another flat flex cable connected display, because of last year we had a PCB that had this for the dashboard, and it caused a lot of errors. But we decided that if we were to route the cable in a more mechanically supported way, that we wouldn't have the same problems that we had last year, where we actually ended up having to twist the cable to get it to work properly in the dash. So because of that, we've opted to use this EVE3X 35A IPS display. It's quite small, and it fits well in the wheel. All right, now to the next part of the project. Now this is where my path and Will's path diverge, and I'll be going over exclusively the steering wheel from this part onward. So for the PCB layout and design of the steering wheel, it was a really odd shape, and it created a bunch of interesting challenges in the PCB design, and made me as an electrical engineer think more along the lines of a mechanical thought, which I found really interesting. So there was a lot of really weird tight tolerances in certain parts of the board, and a lot of extra space in other parts of the board. And then placement challenges with the rotary switches. We had them really close to a lot of these other really important components like the oscillator, CAN transceiver, and that sort of thing. So we had to route things in a really interesting way. And then the other thing we had to think a lot about is mechanical stresses on the board. We had to think a lot about, okay, how can we support specific parts of the board? And I think most of the challenge here was not the actual tracing. It was rather the placement of the components to be ergonomic, to be structurally sound. These two designs on the right, this first one on the top was the first draft of the steering wheel PCB, and this is before I laid out traces even, but rather just component layout. As you can see, the rotary switches, which are those big circles, are on the bottom of that board, but we actually moved them up into the middle of the second board and we were able to reduce the footprint of the board by quite a bit by doing that, and also improve the accessibility for the drivers. Some of the design roadblocks we had were, yeah, we changed the board shape a bunch of times. There were some issues transferring the CAD model into a file that I could read with my Altium software, and that had some issues, but I was able to work around that. And then we rearranged the component placement, like I was talking about with the rotary switches, and then we added 10 new solder joints during this process. We realized that we did not have a specific way we were going to connect to the connectors, and we wanted something that would be very, very low profile. And so in those on this board, you can see that there are those sort of circles on the top and bottom right of the final draft of the steering wheel PCB layout, and those are so that we can attach Autosport connectors to the outside of the enclosure, and allow for a very, very low profile connection. On the bottom right of that board, we also decided to add another Autosports for programming header, as well as those necessary connectors like that CAN interface and the power on. What I learned from these roadblocks was definitely that communication is incredibly important between the EEs and MEs, especially for these projects that have very small or very intricately connected electrical and mechanical systems. And in this case, we had the PCB, and then we had the enclosure, we had the back plate of the enclosure. The front plate of the enclosure was made out of 3D printed plastic. The back plate was made out of carbon fiber. We had custom made grips that we had made by scanning actual imprints that the drivers had made with their hands. There was a lot of very complicated systems. There's big holes in the board to account for the way we mount the steering wheel to the steering column. And then the other thing that I learned was definitely that PCB is designed as an iterative process, and you really need to be communicating at every single step. And multiple times I had found myself working a little too far forward and then having to go back and completely change my design. So going forward, I definitely would prioritize communication with the other engineers and try to stay on the same page with them immediately. The first step of manufacturing was the surface mount components. After we ordered the PCBs, we had to build them. So to populate the PCBs, we would attach all of these components. And the way we did that was we would collect all the components into one place that was easily accessible. And we would lay a stencil down, apply solder paste using a stencil and a card. And then using a magnifying glass and tweezers, we would place each of the components in place by hand. And then during this process, you really want to be making more than one, because the amount of effort that it takes to go and find each component every time really adds up. But if you have multiple boards you're making, so I made 2 at a time rather than 1, you can really improve that time. Inspection. So for inspecting, you really need 2 or more people, and I'll talk about that later in my kind of roadblock section. And then finally, you bake it in the reflow infrared oven, and that allows for that solder to connect all these pieces to the board. For the second part, this is a little bit more interesting because we needed to make sure that the buttons were perfectly aligned with the board and the enclosure. So what we did is we set the buttons in the enclosure and then laid the PCB on top and soldered them in after. So as you can see, I had to install the button later on, and I took some pictures. That button in the top right is how it would be installed. And then you lay this PCB on it and you solder the back with a soldering iron. Some of the roadblocks we found were missing components, solder bridging, and mechanical enclosure errors. Missing components are pretty easy to fix with a soldering iron. We had only one. It was that C4 capacitor. It was really no big deal. And then solder bridging, we had some solder bridging on one of the PCBs that was where solder connects pins on the microcontroller. So you come across it with flux and a soldering iron, and it will spread back out and it will fix that error. The biggest error that we came along was with mechanical enclosure. We did not 3D print the prototype before professionally manufacturing it, which meant that we received a professionally manufactured piece that didn't fit. Our rotary switches were a different depth than our buttons, and so because of that, we had no way of attaching those rotary switches to the front of the panel. So we had to take a whole 3 weeks to reorder that component before we could finish manufacture. And then, yeah, the other thing was just missed components. That sort of thing can be easily fixed by having more than 1 or 2 inspectors. So going forward, that would definitely be the things that I would want to do next time. So this is where the paths kind of diverge. there's sort of programming firmware going on and manufacturing going on at the same time. So this is the firmware part. So this, I was not completely alone in designing the firmware. Pavlo had done a lot of the lower level setup and system design, and my job was to design the displays as well as look for CAN signals to display on the display, and then lastly like button pressing logic to cycle through pages. So it's almost exclusively just related to the display because that is like a very time consuming thing, and Pavlo wanted someone else to do it instead of him, which I totally understand. So these are some of the pages, and on the bottom left I have a little bit of the code that I wrote. But yeah, these are 3 of the pages that I designed for the steering wheel. Yeah. Some of the firmware roadblocks. Most of the firmware was just learning about how to write firmware. So it was a lot about understanding the structure of how GFR writes firmware, how like more larger organizations write firmware. I had to learn how to use the display editor software, which is a proprietary software of the manufacturer of the display. And then I also had to use new C++ libraries that I had not used before, and then lastly, Git and GitHub repositories and how to work with Git. This is the first time I've interacted with that sort of system, which is really important, that I'm happy that I got those experiences. Testing. So testing was used to validate the whole functions of the PCB, and by testing each individual subsystem, you can be able to confirm that the system will function within the car. So this is on the bottom right, my CAN and power on test setup. It's kind of messy, but it was super useful for doing multiple tests at once. So the computer is used to read CAN signals, and there's 2 power supplies on the left, those big black blocks, and then we had the PCB on the right. So for the dashboard, we had a power on test, a CAN commutation test, and then a button function validation, rotary switch accuracy, and then just testing the display. So some of the roadblocks that we had were rotary switch accuracy. It did not match the simulations I had done earlier in the term, and it was able to be fixed in firmware. But next year, setting up a resistor network and actually simulating it, or actually running it with those rotary switches, I think would be a good idea. Or even just ordering a very early PCB that just works with those rotary switches might even also be the solution. See if it works. It wasn't a super big issue. And then for the display, there were 2 issues. Everything else checked out. But the display, it was only showing text without other design assets. We ended up changing the coordinate system within the firmware, and that seemed to fix it up. And then the pages are swapping in reverse directions with button presses, which is a really easy fix with firmware. Otherwise, testing-wise, everything went really, really well. So, as a part of the conclusion, and going forward, this project was completed and operational from an electrical standpoint. We have a functioning display, operating buttons and switches, and CAN communication. Going forward, we still plan to pot the enclosure, but we ended up without enough time to pot it before the end of the term. So that will be going into the next term. And then recommendations. So these are things worth considering for the next revision of the dashboard, and this is what I would really recommend people think about. So the first thing to think about is the power electronics in the steering wheel. So because we used a 3.3 volts from the dash PCB, we realized that we didn't need to include that power electronics within the steering wheel. And so next year, I would recommend just connecting that 3.3 volts and forgetting about that power electronics in the dash PCB. It would reduce the complexity of the board, and it will also improve the efficacy of those connectors, because what we ended up having to do was add an additional wiring harness splice for the power that the steering wheel PCB needs. The other thing is changing the dash breakout, because there was a rules change that we needed to think about before adding a dash breakout, because those rules required LEDs need a way for the firmware to detect if they're connected or disconnected. So right now, there's no way for those to do it, and so we have until the end of our American racing season to figure out how to fix that problem before we go to Europe. And so not even going forward to the next year, but even just in the next months, we need to revise that dash breakout system or add some sort of way of having a watchdog added. And then lastly is just record and observe how the drivers interact with the driver ergonomics of the wheel, and see if there are problems or suggestions that they have or requests that they have, because that was where a lot of the design from this term and this project came from, is just asking drivers what they want to see in the wheel. Yeah. And then my personal takeaway: this project has taught me a lot about working in a larger team, and how to work with other types of engineers. I learned also a lot about mechanical enclosure design, and learned a little bit about how encapsulation works, and like what types of things you're looking for different projects, for like resins and silicons and stuff from my potting research. I also learned about the kind of larger structure of firmware design projects and Git and that sort of thing, which I found incredibly useful. And then I also learned more about how you design tests and validate systems in a larger scale field. Overall, GFR was an incredibly informative experience for me. Thank you. Thank you for watching.